Years ago, in the summer of 1925, our view of the universe changed forever. A young German scientist, Werner Heisenberg, was famously recovering from a bout of hay fever on the treeless island of Helgoland in the North Sea, a barren island. And while recuperating, he came up with the mathematical framework that today we call quantum mechanics. I've been obsessed with quantum mechanics myself for over 4 decades. In fact, the first Friday evening discourse I gave was 21 years ago on quantum mechanics. It was about a year after I had published a book on the subject, Quantum, A Guide for the Perplexed. I always tell people who read it, I say, I can't promise that you will be any less perplexed when you read the book. You'll just understand why you're perplexed. In fact, on the back cover of the book is the famous quote by the great Danish physicist Niels Bohr, who says, if you're not astonished by quantum mechanics, then clearly you haven't understood it. Now, what I want to do in this lecture is several things. I want to give you an outline, a brief history of the subject, why it is so perplexing and so weird, but also why it's the most powerful theory in the whole of science. In fact, I should correct that. Quantum mechanics isn't a theory. Quantum mechanics is a framework a mathematical framework for understanding the workings of the microcosm, the subatomic world, the world of atoms and beyond. In the same way that classical Newtonian mechanics isn't a theory. Again, that's a framework for understanding the workings of our everyday world, forces and momenta and energy and so on. Quantum mechanics is its equivalent down at the micro scale. And it's very different. It's very counterintuitive. And yet it's powerful and it's successful, and we've built our modern world on it. So I want to start first with a little bit of history. I don't want to go, I've got 1 hour to cover a lot of stuff. So I'm going to whiz through a bit of the history. But I guess for many of you, if you know something about quantum mechanics, then you probably know some of these names, some of the great quantum pioneers, going back before 1925. In fact, the original quantum theory, the original seed of the idea began in the year 1900, thanks to another German physicist, Max Planck. Planck suggested that radiation given off by warm bodies isn't continuous, like the stream of water from a tap, but if you look carefully enough, it's discrete. It comes in lumps, like separate drips. A few years later, Einstein extended that idea and said that actually all electromagnetic radiation, light, in all its wavelengths, ultimately can also be thought of quanta particles of light, which we now call photons. Other physicists got interested, got involved. Niels Bohr himself, the Danish physicist, extended the idea to describe the energy of atoms, or more correctly, the energy of electrons as they arrange themselves around the atomic nucleus. This was very soon after Ernest Rutherford had given us the very first inkling of what an atom looks like. Mostly empty space, a tiny dense nucleus in the middle with electrons around the outside. That was a picture of the atom that looked like a miniature solar system, which we soon discovered wasn't really quite correct. But the idea, this quantum theory, the idea of things are quantized, the energy of the electrons around the atom also comes in discrete levels, discrete values. Electrons couldn't have any energy they wanted. Others, like the Frenchman Louis de Broglie, talked about waves could behave like particles, particles behave like waves. Things were starting to get a bit weird. You had people like Max Born, another German physicist, Wolfgang Pauli, the British physicist Paul Dirac. What we're celebrating this year as International Year of Quantum Science and Technology is 100 years since the invention of the full quantum mechanics as it evolved from the old quantum theory, which is due to not just Heisenberg, but an Austrian physicist, Schrödinger, he of the famous cat in the box that's dead and alive at the same time. More of that later. Heisenberg and Schrödinger both developed mathematical approaches to understand the atomic world, but rather different in their approach. But it was soon discovered that they were actually equivalent. And today, when we talk about quantum mechanics, when we teach quantum mechanics to students, we use a mixture of both. Quantum mechanics culminated in this famous conference, the 5th Solvay Conference on Physics, held in Brussels in 1927. Very often, this photograph is regarded as the most intelligent picture ever taken. Now, the physicists among you might enjoy, and no doubt have done in the past, try to figure out who all these great names are. Of course, everyone recognizes Einstein in the front row. Marie Curie, the only woman in the whole photograph. However, she has something over the rest of them. She won 2 Nobel Prizes. None of them managed that. But of course, you know, you have Henrik Lorentz, you have, look, there's Niels Bohr. Niels Bohr at this point is only in the secondary. He's not even one of the grandees yet. But then you get the young guns, Heisenberg and Pauli and Schrödinger. Anyone who was anyone working in this new theory of the atomic world was at that conference. And often the way history is taught, it's suggested that quantum mechanics was complete. It was finished. They'd sorted it all out. Now let's go and use it to understand physics and chemistry and build the modern world by this time. Famously, the 1927 Solvay Conference was also a time when the 2 giants of the field, namely Einstein and Niels Bohr, had their famous debate about the nature of reality. And simplified versions of history would say, well, look, Bohr won the argument. Bohr had his famous institute in Copenhagen, and his view, together with his group of young geniuses, Heisenberg and Pauli, created what we today call the Copenhagen picture, which is a view of reality they argued was forced upon us by the mathematics, by the theory, and by experimental evidence, which suggested that the atomic world wasn't something that we could picture. We couldn't talk about an atom as a miniature solar system with electrons buzzing around nucleus. You couldn't even imagine what an atom was like. It was maths. It was abstract. What quantum mechanics could give you, they argued, was predictions about the results of measurements if you were to look. And so, well, if you look to see what an atom is doing or where an electron is, then this is what quantum mechanics tells you will find. And sure enough, that's what they found. And quantum mechanics explained so many experimental results, which until then people hadn't been able to figure out. It turned out quantum mechanics got it right. But at its heart, there was this mystery about, really? Can we really not understand what's really good? Can we not have a picture? Einstein famously said, if everything ultimately is made of quantum particles, then is the moon not there when I'm not looking? Do I only bring it into existence when I observe it, as you're telling me happens when I observe atoms? Well, people working in quantum mechanics, yeah, well, that's philosophy, right? Let's get on with things. And they did. If you think about the progression of quantum mechanics throughout the 20th century, we start with the old quantum theory of 1900. By the 1920s, we have fully fledged quantum mechanics. By the late 20s, people like Paul Dirac were already developing advances on quantum mechanics, saying, well, the other big theory in physics is relativity theory. So special relativity, the idea that nothing can go faster than light, E equals mc squared, and all that business, time is the fourth dimension. People like Paul Dirac started to connect that with quantum mechanics. And we get the early ideas in what's called quantum field theory. That develops by the 1940s. People like the great American physicist Richard Feynman, together with Schrödinger and Tomonaga, they develop what's called quantum electrodynamics, which is quantum mechanics applied to all matter and all electromagnetic radiation, light and stuff, how they interact together, their properties. Quantum electrodynamics is often regarded as the most accurate theory in all of science. Very, very powerful. Pretty much most of the phenomena, apart from gravity, that we see around us today, we can describe using quantum electrodynamics. And then physicists went further. They said, well, there are other forces in nature trapped inside the atomic nucleus, what are called the strong and weak nuclear forces. And pretty soon, certainly by the 1960s, they'd combined one of those forces, the weak nuclear force, with quantum electrodynamics. Bring them two together, and then there's another even grander, more unified theory called the electroweak theory. They didn't stop there. They said there's another force inside the nucleus called the strong nuclear force. What if we apply quantum field theory to that? And they developed what's called quantum chromodynamics. Then all these ideas brought together by the 1970s in what we call today the standard model of particle physics, an umbrella term that describes the physics of, as far as we know, all the forces of nature, all the phenomena that we experience, apart from gravity. And today, and certainly for the last few decades, the big challenge in fundamental physics is how do you bring gravity in? That's the last remaining big phenomenon in nature that hasn't come under the spell of quantum mechanics. Well, physicists carried on using quantum mechanics. It worked, it was powerful, they developed more advanced theories, but not everyone was happy. Einstein, for example, still hadn't quite given up the battle. He, despite being a revolutionary scientist himself, coming up with his two theories of relativity, he was reluctant to embrace all the predictions and implications of quantum mechanics. In the mid-1930s, he published a very famous paper, together with two colleagues, Boris Podolsky and Nathan Rosen. The title doesn't really tell you much. It just sort of, it's a question, and it suggests they're not happy with quantum mechanics. But it's famous because it's known as the EPR paper, named with the initials of the three authors, Einstein, Podolsky, and Rosen. And from it, within the paper, they outline their issue with quantum mechanics, which today we refer to as the EPR paradox. I want to explain this because it comes back again when I talk about our quantum technologies moving forward. So what is the EPR paradox? Well, imagine, I'm going to simplify it, may not be exactly the way they explained it in their paper, but and you can look it up online, there's lots of ways of explaining it. But imagine you have some device that produces two particles of light, two photons, and it sends them out back to back, equal and opposite momenta, equal energies. I've depicted them here as what are called wave packets, photon 1 and photon 2. A particle of light, if it's confined in space, then it's showing its particle-like nature rather than its wave-like nature. Now we know that light also behaves like a wave. In fact, here on the desk is the first volume of the books by Thomas Young, regarded very often as the last great polymath. He just did everything. But he, over 200 years ago, here at the Royal Institution, showed that light behaves like waves. His famous two-slit experiment with light, showing the interference pattern as light passes through two slits. And there are lovely pictures in this book, early 19th century, showing that light behaves like a wave. Well, Einstein had showed that light also behaves like a particle. So here I am trying to cover both Young and Einstein's pictures of light. It's sort of a particle because it's sort of confined, it's not spread out to infinity, but it's also wiggling like a wave. This is what's called a wave packet. Excuse me while I have a drink of water. I recently recovered from a cold. I haven't had any Lemsip today, so that's always a sign that I'm recovering. I'm addicted to the stuff. As soon as I get a cold, I can have Lemsip now. But I just need a sip of water. Right, so photon 1 and photon 2 come out. Once they're some arbitrary distance apart, arbitrary means I don't care. They could be a few meters apart. They could be on either side of the Milky Way. It's irrelevant. They're far enough apart that you'd hope that they're doing their own thing separately. What if we stick some instrument onto photon 1 to measure its wavelength? Now, if you're measuring the wavelength, or the frequency, or the color of the photon, that means you're probing its wave-like properties. It's not a particle. Now, the quantum mechanics, the lesson is that what you get depends on what you measure. If you want to see it behaving like a wave, sure enough, it'll oblige and behave like a wave. So if you know the wavelength, the color of photon 1, and since wavelength or frequency is proportional to the energy, and you know photon 2 has the same energy, therefore the same wavelength, you instantly know without measuring anything to do with photon 2, you know what its wavelength is. It's behaving like a wave. However, we could instead have used a different instrument that measures the position of photon 1. That is, its particle property. And if you know where photon 1 is, photon 2 will also be behaving like a particle in the sense that they have equal and opposite momentum. So by measuring the location of photon 1, we would know the location of photon 2. Now, the point here is that, as Einstein and his colleagues suggested, sure, when you are measuring photon 1, the way it behaves depends on what you measure, and also you inevitably disturb it as you measure it. You can't reliably say what it was doing before you measured it because you've interacted with it. But no one's touched photon 2. And they argued that they could know, or could have known, both the position and momentum of photon 2 without interacting with it. How could it possibly have that? It must have had those properties from the start, which seems reasonable. The nice example in our everyday world would be, were I to have a pair of gloves, a left glove and a right glove, and I put each one in a separate box, turn my back, and then someone takes one of the boxes away, far enough away from me. I don't know whether I've got the left glove or the right glove. But as soon as I open the box, I see I have the left glove. I know instantly that the other box contains the right glove. But what's changed is just the state of my knowledge. It was always the right glove. I just didn't know it. In the quantum world, this isn't what is argued is happening. And Einstein didn't like that. So their argument was that there would have to be some sort of interaction across, presumably if they were far enough apart, the entire width of the Milky Way galaxy, for photon 2 to know that you're measuring the position of photon 1 or the wavelength of photon 1 in order to change its property accordingly. Surely it can't do that once the measurement is made. It must have had those properties right from the start. That's the only way that it makes sense. Quantum mechanics says differently. Quantum mechanics says photon 1 and photon 2, neither of them have decided whether they're a particle or a wave. Not only that, but they are combined together. We say they're quantum entangled. They're described by the same quantum state, a single quantum state that tells us the nature of both photons. A single photon can behave like a wave or a particle, and until you measure it, it's neither. It's both. It's a mixture. The same with photon 2. Forcing photon 1 to make up its mind affects instantly what photon 2 is doing. Quantum entangled. Well, the EPR paper isn't about the fact that you can't know the position and momentum of a particle at the same time. That's what's called the Heisenberg uncertainty principle. Einstein wasn't happy with that to begin with, but he'd sort of come around to the idea by 1935. That wasn't his issue. His issue was that photon 2 must have had this property right from the start. The fact that if quantum mechanics said it didn't, then there was something missing in quantum mechanics. Okay, that it was incomplete. In fact, in the last paragraph, the last sentence in their paper is, well, we have thus shown that the wave function does not provide a complete description of the physical reality. We left open the question of whether or not such a description exists. We believe, however, that such a theory is possible. The likes of Niels Bohr said, no, let's get on with it. It's not possible. That you can only describe these two photons, however far apart they are, by a single quantum state. Well, the paper made a splash. In fact, it made the front page of the New York Times. In 1935, Einstein attacks quantum. No mention of the other two authors of the paper, Einstein and two colleagues. Einstein, by this point, he's the most famous scientist in the world. He's going to get credit for it. But in fact, Einstein didn't write that paper. It was Boris Podolsky who'd written the paper. And Einstein was unhappy, to say the least, that Boris Podolsky then leaks it to the New York Times as well. So he didn't like the idea that it was being publicized in this way, not because he didn't agree with the sentiments of the paper, but it wasn't really his work. Another physicist who sided actually with Einstein was Schrödinger, Erwin Schrödinger, the Austrian physicist. That same year, not long after the EPR paper comes out, he wrote a three-paper set of articles in Nature. This is where he first describes his famous cat in the box, the cat that's dead and alive at the same time until you open the box to look. Now, Schrödinger's problem wasn't about incompleteness of quantum mechanics. It wasn't about the uncertainty principle. It was about what happens when you make a measurement. How does this thing that can be fuzzy and weird and doing lots of things at once suddenly give you a concrete answer when you look? What is it about measurements? And so he uses the cat as an example. How can the cat be dead and alive at the same time? What's important in the context of what I want to say is that that's the paper where he first introduces the word quantum entanglement. Verschränkung is what he calls it in German. In fact, a few years later, Einstein writes a letter to another physicist, Max Born, and he complains about what quantum mechanics says is going on in his EPR paper. And that's where he first uses the term spooky action at a distance. Spukhafte Fernwirkung. It's perfect German as far as I'm concerned. Because how can photon 2 and photon 1 be instantaneously communicating with each other? And photon 1 saying, they've just measured my position, you better be a particle. Oh, no, they've measured my momentum, you better be a wave. Einstein said, how can that? Surely nothing can communicate between the two faster than the speed of light. But in the quantum world, that seems to happen. That is quantum entanglement. And we're going to see later on how quantum entanglement is helping us in our revolution, the technological revolution today. Quantum foundations in the 19th, well, most physicists had sort of resigned themselves to the fact that Bohr had won the argument, get on with it, quantum mechanics works. Einstein was somehow the reluctant, old hand who was sort of dragging his feet, not wanting to accept quantum mechanics. There were still very powerful physicists in the 1950s, people like Eugene Wigner and John Wheeler, who were at least prepared to think about, is it completely answered? Are we happy that we understand what's going on in the quantum realm? they were certainly more sympathetic to young scientists who dared, and I use that term sort of quite literally, they dared to argue against the Copenhagen school, people like David Bohm and Hugh Everett. They came up with alternative theories that would explain the EPR paper, that would explain the cat-in-the-box thought experiment, that went against the Copenhagen view, which said, all that matters are the results of measurement. Quantum mechanics predicts what you will get when you make a measurement, and you can't say anything about what's going on when you're not looking. Just do the maths. So these were mavericks, outsiders. Another maverick outsider in the 1960s was the Irish physicist John Bell. Now, John Bell famously didn't like the Copenhagen view. He talks of a time when he was caught in a lift with the great Niels Bohr, and he says, I just didn't have the courage to confront him about the Copenhagen view and say I wasn't quite happy with it. Well, many years later, in the late 80s, I was caught in a lift with John Bell. This was at an American Physical Society meeting in Baltimore in 1989. I was finishing my PhD and looking for postdoc positions in America. And I'd just come out of a talk on quantum mechanics given by someone who clearly was promoting some new idea which I thought was nonsense. And I got in the lift with John Bell. And unlike John Bell, he didn't have the courage to confront the great Niels Bohr. I had the courage because I agreed with John Bell. So it was easier. So I said, that last talk, I knew he'd been in the talk as well. That last talk, yeah, and he said, yeah, I agree with you. Has he not heard of such and such? He obviously doesn't understand quantum mechanics. So I felt very pleased that John Bell and I both agreed on this matter. Well, long before that, in 1964, John Bell had come up with a theorem which no one really had thought possible. It was a theorem that would essentially work out, was Bohr right or was Einstein right? This is often regarded as the most profound discovery in science. He said, if Einstein's right, if nature is local, now local means you can only interact with things close enough to you, and if it's far away, then you need some time before you can influence it. Time, the fastest you can get to it is by sending a light signal. And you can't interact with something instantaneously if it's too far away. He said, so if Einstein's right and nature is local, then there's a formula that says there's only so much that's like, for example, the EPR photons, there's only so much those two particles can have in common, given that they were both at a single origin. They started off together. A left and right glove, for example. They can't then change what they're doing when they're far enough apart unless they have enough time to tell each other what's going on. He said, this formula, it was formed as an inequality. Four other physicists, Clauser, Horn, Shimoni, and Holt, called the CHSH inequality, put it in a nice, neat mathematical formulation that allowed experimentalists to go away and check it. Once and for all, can we shut Einstein up? I don't really want to go into the details of it. I just had to add those words so that I can explain. I don't like putting a formula on when I'm giving a lecture without actually defining what the symbols mean. But essentially, these capital E's, these are what are called correlations in how much to the two photons you're measuring their polarization. So light can be polarized in different angles. So you've got detectors now, rather than the EPR one where you're only looking at one photon, what if you have detectors measuring some properties of both photons? And you swivel these detectors around, like you've got Polaroid lenses and glass, and you can twist them around, and you get the light. Sometimes it's blocked in some angles, and sometimes it's allowed through. This is an experiment that suggests that if those two photons in the EPR picture only have in common what they had in common when they started, they shake hands and say, I'm doing this, I'm right, bye, see ya, and then when you make the measurements, if that's all they can have in common, then there's an equality. This quantity here cannot be greater than 2. So if you measure these things in an experiment and you get a number more than 2, they must be communicating after they've left. There must be some what's called non-local connection between them, instantaneous quantum entanglement. Well, that experiment was first done by John Clauser at Berkeley in the early 1970s, then repeated in the early 80s by Alan Aspect and his collaborators in Orsay in France, and then many other experiments, particularly by an Austrian physicist, Anton Zeilinger, and in fact, all 3 of those men had to wait a long time. 2022, they won the Nobel Prize for tests of Bell's inequality. What do they find? Quantum mechanics is right. You get a number more than 2. Einstein couldn't be right. Quantum entanglement, however weird you might think it is real. Quantum ideas and some of these weirdnesses of quantum mechanics continue to this day, and in fact, only this year, 3 other quantum physicists won the Nobel Prize for Physics for another weird aspect of the quantum world, namely quantum tunneling. Okay, well, I want to move on to what is weird about quantum mechanics. I want to go through this quickly because, what to say? Superposition and interference. Now, superposition and interference are properties of waves. Thomas Young would have been very clear about light waves, but we can think of water waves or sound waves behaving in this way. When we say waves superimpose on each other, we mean this sort of thing. Drop 2 pebbles in water, and the waves, the concentric circles that move outwards, will overlap, and you start to get some sort of weird, crests and troughs cancelling out and superimposing and so on. That's what we call interference. Well, in the quantum world, particles also can have this interference effect. But it's a superposition, not of waves. You can have superpositions of particles, for example, having 2 energies at the same time, or being in 2 locations in space at the same time. If you think about a light switch that's on, so for US audiences, that would probably be off. I don't know why they have it the wrong way around. They drive on the wrong side of the road, and they don't know how to fix their light switches. So that'll be on, and that'll be off. In the quantum world, it would be the same. It would be like having something that is both on and off at the same time. The cat that's dead and alive at the same time. But we don't worry about cats. That was a thought experiment. What we're talking here about is objects down in the quantum realm. Particles, electrons, photons, atoms, and so on. And there can be, what we say, there can be in different quantum states, so they can have different values of energy and so on, and not just 2, not just on and off. They can have multiple states at the same time, and you can have lots of particles all together, all being in a superposition at the same time. These sort of weirdnesses were known about and understood right from the early days of quantum mechanics, and this is what we mean when we say quantum mechanics is perplexing and counterintuitive. My famous example is the quantum skier. The tree looks fine. There's no reason not to think he could father children. Hasn't done him any damage. But you see something like this, no, that's impossible, right? In the quantum world, that's what happens. Famously, it's what happens in the 2-slit experiment. Now, Thomas Young was the first to carry out the 2-slit experiment for light, but we now know we can do the quantum version of it using not light. You can use it using light, but you can also do it using atoms. I'm not going to go into this in detail, and I'll explain why. My last Ri Discourse was in 2013, and there I am, talking about the 2-slit experiment. Now, I explained how it went, and I went through all the stages of how weird and wacky and like, exploding brain it is. And then I made a mistake. I said, anyone in the audience who thinks they have a common sense explanation of how the atom gets, what single atom, so this is with light, But I then go on to show with atoms, firing one atom at a time, you still get the interference pattern. How does the atom go through both slits at the same time? It does, but then if you look to see where it's going, it seems to only go through one or the other. It seems to know if you're spying on it. And I said, if you have a common sense explanation, get in touch with me because the King of Sweden might want to give you a phone call. To this day, I don't know why I thought the King of Sweden would be very, would listen to my recommendations from sort of random people. Give, Your Majesty, give that chap a Nobel Prize. He's sorted out. But my real mistake was I gave a lecture in this Faraday lecture theatre talking to a few hundred people, forgetting that the lecture was being streamed online and then goes onto the Royal Institution YouTube channel. That clip has been viewed several million times. To this day, 12 years later, I get 1 or 2 emails a week from people saying, I have solved the two-slit experiment, give me my Nobel Prize. And I had to think, oh, no, you haven't solved it. Sad, but, it's great that people are thinking about science in this way, but not so great when they think that they've solved a problem that many people have thought very hard about and can't really figure out a common sense view. So quantum tunneling is another aspect of the quantum world that's strange. The example that I like to give is, and many people like to give, is if you have a ball and a hill, you have to kick the ball up the hill hard enough if you want to get it to the top and over to the other side. If you don't kick it hard enough, it's going to go halfway up the hill and then come back down again. In the quantum world, replace ball with atom or electron or whatever, and replace hill with some energy barrier. You can give that atom, say, enough energy to get halfway up the hill, and it won't roll back down again. There's a certain probability that it gets halfway up, disappears, reappears on the other, and rolls down. Like a ghost phantom walking through a solid wall. If we saw it in our everyday world, we'd say, that's ridiculous. You've clearly lost the plot. You're not doing science now. You're just doing silly stuff. Quantum tunneling is real. Not just because the guys won a Nobel Prize for it this year. The reason we're here today is because we get life. Life gets energy, light, and warmth from the sun. And the sun shines because of quantum tunneling. Hydrogen nuclei, protons, can quantum tunnel together in the first step towards nuclear fusion to make helium, and that's what creates a thermonuclear fusion, the energy of the sun. So the sun shines because of quantum tunneling. How do we talk about it in quantum language? Well, it's basically particles are waves, and waves can leak through the barrier. So there's a certain probability. So part of the wave bounces off, and the other part travels through. What is it that this tells us? Well, it gives us the chances, the probability that the particle is going to get through. And that probability depends on just how big the wave is that passes through. The maths all works, you see. And the experiments that we do to check the maths all agree with what the maths predicts. It's the logic, the common sense picture that we struggle with. Okay. And then there's quantum entanglement. Remember the EPR, spooky action and distance. Quantum entanglement was seen to be, for many years, this really extremely outlandish, counterintuitive aspect of quantum mechanics. It's far weirder than quantum tunneling or quantum superposition and interference. Today we know that entanglement is so prevalent that it's probably the most important feature of physical reality. We still don't teach quantum entanglement seriously to undergraduates in physics at university, and I think we should, because it is so important. And current theories in the fundamentals of physics are even suggesting that quantum entanglement may be the source code base of reality. Even time and space themselves may emerge from quantum entanglement, is one suggestion. But more importantly, many of the technologies I'm going to mention in a moment rely on quantum entanglement. and use quantum entanglement. So it's not just weird. It's, however weird you might think it is, it's being used. We're developing devices that are going to benefit humanity because quantum mechanics is real. Okay, an entanglement comes along with something else called decoherence. That's its annoying little brother. Decoherence is when our everyday world messes with, disturbs quantum entanglement. Quantum entanglement, the two photons back to back, that's a very delicate quantum state. If you measure it, you open Schrödinger's box, for example, or you detect whether photon 1 is a particle or a wave, you destroy the entanglement. You force the other particle to do what it's told, what it should do, to complement the first one. So decoherence destroys entanglement. Decoherence is something that was developed mainly by Dieter Zeh and Wojciech Zorek up to half a century ago now. It's a very well-developed idea in physics. It solves things like the Schrödinger's cat paradox. Now we understand a lot more about decoherence and entanglement. Okay, part 3. What have we done with quantum mechanics then? Well, in physics, of course, we've used quantum mechanics to understand the structure of matter. We understand, so the cartoon of the atom with electrons orbiting around it is wrong, but we still use it to somehow depict the atom in a simplified way. We understand the nucleus of the atom is made of protons and neutrons, and the protons and neutrons are made of quarks and gluons. We've built larger and larger particle accelerators to smash matter together at ever higher energies to break it up into tinier and tinier constituents, and we arrive at the standard model, which I mentioned earlier, which tells us the building blocks of matter as far as we know so far. There are still a few things we've got to iron out, like what is dark matter and what is dark energy. But anyway. So that's physics. Chemistry. This is a modern periodic table of the elements, as you would see on any school wall in the world. A modern one because certainly it's far more modern than Mendeleev's original periodic table from the 19th century. He only knew about half the elements that we know of today. But this one contains lots of new elements you may not even heard. So this OG is the heaviest element synthesized, oganesson, element 118. The reason why the periodic table is classified in this way, according to the physical and chemical properties of the elements, is because of quantum mechanics. Quantum mechanics explains the rules for how electrons arrange themselves around atomic nuclei and give us the properties of the elements. Without quantum mechanics, you wouldn't understand why and how the periodic table looks the way it does. In terms of technology, of course, what we now call the first quantum revolution involved developing many devices that relied on these ideas in quantum mechanics. The laser is a famous one, but of course we have the diode, LEDs, integrated circuits, the computer, GPS, internet, GPS, smartphones. Everything that we sort of rely on and take for granted in our everyday world relies on our understanding of the quantum world. Without that understanding of the quantum world, we wouldn't have any of these things, let alone things like the electron microscope, the photomultiplier, which is a device that many of you will not have even heard of, but is used in so many other instruments. MRI machines, they're quantum. It's not just sticking a patient in a strong magnetic field. It works because of quantum mechanics. All of these, in fact, the whole of modern electronics is really thanks to our understanding of the quantum world, because it gave us an understanding of semiconductors, and semiconductors, the understanding of chips, and so on, and we have computers. All of that relies on the quantum mechanics that was developed in the early 20th century, quantum tunneling, quantum interference, and so on. But we now have a second quantum revolution. Sometimes it's called quantum 2.0, but that suggests there's a 3.0, and it's like Windows. It's not. It's the second quantum revolution, and I want to go through a few of the technologies that are emerging today because of this revolution. Quantum timing is the first one, by which I mean quantum clocks. The atomic clock. Now, the original atomic clocks, they rely on an early feature of the quantum world, namely this idea that electrons and atoms can't have any old energy. They can't orbit around in any distance from the nucleus. They have to have discrete energies. And that is used in order to generate, in the early atomic clocks, light, microwave radiation coming from a certain type of atom that you can measure the wavelength of very, very accurately. And if you can measure the wavelength as how many waves pass through a certain point, that gives you a counter. It gives you a way of measuring time, not a pendulum swinging or quartz crystal vibrating, but microwave radiation emitted by atoms that pass through this what's called an optical frequency comb. And that gives us very accurate timing to tiny millionths and millionths of a second. These sorts of atomic clocks are the basis of global navigation systems, GPS systems. The reason your smartphone, the reason you can use Google Earth and find out, or Google Maps to find out where you are, because those satellites that are sending radio signals to your phone have atomic clocks on board. And those atomic clocks are needed to measure time very, very accurately in order for us to measure the distance from those satellites very accurately, because that's the only way you can triangulate where you are. Atomic clocks over the last decade or two have been miniaturized, as do many technologies. Here's one alongside a single coffee bean. But also, they're becoming more accurate. So there are now what are called optical lattice clocks. These are atomic clocks that use lasers to pump energy into atoms, and then those atoms give off that same energy very, very precisely, but it's not in the microwave region of the electromagnetic spectrum. It's much higher energy in the optical region. So higher energy means higher frequency. Higher frequency means more waves passing through this counter, the checkpoint, and that means much more accurate timekeeping. The talk now is that these atomic clocks are so accurate, they lose something like less than a second over the age of the entire universe. I mean, just ridiculous accuracy, and yet it's needed for many technologies, that level of accuracy. There are even now advances in rather than atomic clocks, but nuclear clocks, looking at pumping the nucleus of the atom with energy and seeing how that gives off its energy at much higher frequencies to give even more accuracy. Okay, quantum imaging and quantum sensing. These are fun advances in technology. Quantum imaging, well, the example I wanted to say, I want to go through these relatively quickly. So ghost imaging is this wonderful idea where you can look at something, well, you're actually not looking at it. You send light to probe it, and then light in another direction goes to a camera, and in the camera is the image of the thing that you weren't looking at. I know. I mean, it's crackers, right? But it relies on this idea of quantum entanglement, the fact that, like the two photons that go back to back, they're still entangled, they're still talking to each other. The basic idea is this. You have some sort of device that fires photons of light, high energy. They pass through a crystal, a material that sometimes, not all those photons, but sometimes can absorb those photons, and then that energy that is absorbed, it gives out again, out the other end, as two photons, just like the two back-to-back photons in the EPR. But what's different here is that these two photons don't have to have the same energy, right, or the same color. So, for example, one can be an infrared photon, and one could be a visible light photon, higher energy. As long as the energy, their combined energy, is the same as the original photon that was sent in, you're conserving energy, and everything's fine. So one could be visible light, and the other can be infrared. They are still quantum entangled. So what happens to one influences what happens to the other. And so if the infrared photon interacts with, and passes through or measures, looks at an object, then we see the image with the visible light photon there, sort of time correlated, which means that when you know which photons arrived and which one it's paired with. This is what's called ghost imaging. And it gets crazier. I'll tell you something about the entanglement camera. So this idea uses entanglement and interference. Remember the two-slit experiment and interference patterns. Well, let me see if I can talk you through quickly. So you've got the photon comes in. So now imagine it's coming vertically rather than horizontally. It goes through a first crystal. This is what's called down conversion. It creates these two photons of different energies. You've got the visible light and the infrared light. They're bounced off mirrors, bounced back again. Meanwhile, another photon has passed through and down converted in a second crystal. And that creates another infrared photon and a visible light photon in the opposite direction. And you get, interference pattern. You see these interference fringes. This is the two-slit experiment fringes, or Young's fringes. You've got the infrared one, and you've got the visible light one. Now, if you stick an object in the path of the first infrared photon, that changes the interference pattern here, but because they're entangled, you get the picture on the other side. It's quite incredible that you're looking at something, seeing something without looking at it. It's not wacky science fiction. This is now being used to pick up tiny details in biopsies of tumors in breast cancer. They can pick up far more detail than you could just with infrared cameras, for example, because visible light cameras are much more precise, much sharper images. It is quite incredible what it can do. Already, these cameras are being developed. Now, a camera that relies on quantum entanglement, what would you call it? Yeah, EntangleCam. Perfect. And indeed, so here's the demonstration device. Here, the researchers at the Imperial College and the University of Birmingham who are working on these ideas are showing it off at this summer's summer exhibition at the Royal Society, just up the road from here. Okay, quantum sensing is another technology that is already with us today. It has many applications. For example, you can use it to measure Earth's gravity very, very accurately. You can even measure it out at sea. With these devices are very versatile, or down underground. There are lots and lots of different applications that we can think of that require measuring Earth's gravity very accurately. How do they work? Well, they work, rather than sending photons through the two slits, they work on what's called atom interferometry. So rather than one photon becoming two and bouncing off mirrors, now you have atoms that are quantum entangled. That's my bum and the microphone touching the table. I better not do that again. On the right is a brain scanner, so like a cycling helmet, using lasers and atoms and quantum entanglement that is so sensitive they can pick up the weakest of magnetic fields, even the magnetic fields created by the firing of a single neuron in the brain. And you can use, and so rather than sticking someone in an MRI scanner, which is very, it's a scary process, laying inside there without moving for an hour, particularly say for young children, but studying lots of neurological disorders by just wearing this cycling helmet, and you'll be able to pick up the brain waves is absolutely remarkable. These devices, these instruments, these technologies are already with us today. Quantum computing, of course, is the famous one, and it relies on this idea that of superposition, that rather than having a logic gate that's 0 or 1, binary digits, now we have 0 and 1 at the same time. Have we built quantum computers yet? Well, we're getting there. Not quite as advanced as the imaging and the sensing technologies. What will they do for us? Quantum computers, I don't want to say too much about them because a lot of this is in the, we've heard a lot about quantum computers, but certainly, if and when they arrive, they're going to help us with drug discovery in medicine, maybe designing better batteries or solar panels, to help combat climate change. They're going to be working in finance and logistics. And for researchers, for physicists and chemists and material scientists, they might be able to help us simulate the subatomic world. It makes sense if you're trying to describe a quantum system that you can use a quantum computer running a quantum algorithm to do the job. Just last year, I published a paper with my PhD student, Lance, and my colleague Paul Stevenson, where we're trying to study the atomic nucleus. So although there's no quantum computer yet, we can use a classical computer pretending to be a quantum computer to see if that gives it an advantage in solving some of these important problems in theoretical physics. How far away then is quantum computing? Unlike sensors and images that we have already, well, there are problems, there are challenges. First of all, you need lots of qubits, quantum bits of information to work. You have to make sure that decoherence doesn't kill your quantum entanglement very quickly. This is something called error correction. We don't even know what to build a quantum computer with, what we make it out of. I'll show you a few examples next. And then the software. We need to write the algorithms that would run on a quantum computer. We have a few, but not many just yet. You'll hear the big corporations working at Google and IBM and others saying, we've done it, we've cracked it, it's here. It'll be here next year or the year after. Realistically, we're talking about 1 or 2 decades away before quantum computers actually arrive. So how do you build one? Well, there are lots of candidates. One of them is using what are called superconducting qubits. So this is a famous chandelier cryostat developed by Google. Essentially, what you're looking at is basically the wiring that cools down the real thing that's doing the quantum computation down to near absolute zero. So this is an example provided by a researcher at the Quantum Center for the Quantum Computing, Nye Baker. This is a 4-qubit quantum processor. These blue squares are the qubits. They're quantum entangled, they're linked together, and you have to feed in information. They do their job, and then they send the information out. A 4-qubit quantum computer is a start. But of course, a lot of these companies are going further than that, and they need more qubits in order to do something useful. A lot of the technology developed here with these superconducting quantum computers it relies on several aspects of the quantum world. For example, superconductivity is something that I haven't had a chance to say anything about. Materials cool down to near absolute zero, lose their electrical resistance in their wiring. And so there's no resistance, so the current can flow through without any hindrance. And that makes it a very powerful device. They're developing their processors with more and more qubits. And this is, I did have I've forgotten the name for this one. There probably people in the audience will know what it is. Anyway. That's the latest processor. There are other candidate quantum computers using light, using photons called photonic qubits. There are neutral atom qubits. So this is another 3D printed model. Another researcher working in quantum computing, Luke Fernley, has loaned this to me. So this is the idea here is that rather than using superconducting wires, or photons, it uses atoms, clouds of atoms, that are cooled down by lasers. So you get the cloud of atoms, usually something like cesium atoms at the bottom. We're using lasers, which are from the first quantum revolution, to cool the atoms down. Then they're sent up, they're held in place by a magnetic field, and then other lasers cool them down further. Then you've got other lasers that move and manipulate them around. Then you've got other lasers that pump them with energy and put them into quantum superposition, and then they do their quantum magic. So all of it is to do with lasers in this sense. And then there are others like like trapped ion quantum computers. So they're like neutral atoms, but an ion, remember, is an atom that's gained or lost electrons. So it's charged. The advantage there is that you can use electromagnetic fields to hold them in place. We don't know which of these quantum computers is going to be the one that ends up being the most efficient, the most powerful, the one that's going to give us quantum computing in the years to come. It's not easy. I mean, look at the mess. I can't even connect my skybox to my TV with the wiring at the back. I don't know how. It's lasers and mirrors and wires, and this is why I became a theoretical physicist, because that would give me absolute nightmares. I want to very quickly then end with talking about quantum communication, quantum encryption. I don't want to say too much about these. Are things in the future. The quantum internet would link computers together. See, I was so determined to finish on time. But the future is very close. It's coming to us very clearly, very fast. Some of these devices are with us today, and I want to end by thanking. I did give a talk on quantum biology as a previous discourse, so I won't have to say anything about that now. But particularly, I would like to thank the IOP for giving me the honor of giving this lecture, culmination of the UK contribution to International Year of Quantum Science and Technology, and it's been a pleasure. So thank you very much indeed.